All right, so today we're going to talk about electric vehicles and emissions with kind of a focus on local air pollution. So we've been talking about emissions in general, right? Whether it's coming from the tailpipe, whether it's coming from power plants when you charge the vehicle. But we wanted to focus a little bit more specifically today on what are the sort of implications of these emissions, and more specifically, making this kind of distinction. So when you combust something, okay, we get all this bad stuff coming out of the tailpipe, out of the smokestack, right? But we typically categorize these into two of these categories. So one is greenhouse gas emissions, and one is local air pollutants. So greenhouse gas emissions, prior to a lot of the movement towards thinking about climate change, are thought to be not that big of a deal compared to sort of local air pollutants, which we know cause health effects, right? So we now know that these chemicals essentially increase what's known as the greenhouse gas effect, or greenhouse effect, which ultimately leads to climate change. And we'll talk a little bit more specifically about this in a moment. And then there's this whole other category of pollutants, which are known as local air pollutants. And these emissions essentially decrease local air quality and are associated with negative health outcomes, right? And so both either negative health outcomes or increased toxicity in the environment. And so, you can think of like acid rain might degrade crops, right? Or NOx and SOx causing respiratory issues. And so these are very different categories of chemicals, even though they're coming from essentially the same source. One is leading to damages globally, and one is leading to damages locally. And that's going to help contextualize how we think about impacts and whether we are trying to look at greenhouse gas emissions versus local air pollutants. Those can be sort of radically different when we think about emissions. Okay, so the one that everyone knows about, carbon dioxide. So this is a greenhouse gas. Essentially, you have some kind of equilibrium here with sunlight that comes into Earth's atmosphere. It's going to get absorbed and reflected by various parts of the atmosphere and by our surface. So within the clouds, whether it's hitting the ground or water, and then the energy that is absorbed by these photons will get sort of irradiated back into space. And so you have this kind of equilibrium of energy coming in and energy coming out. So the way that greenhouse gases work in general is that it's going to alter this equilibrium by making it more difficult for the radiated energy coming back out of the as heat from the Earth to leave out the atmosphere. And by trapping heat in Earth's atmosphere, you will change the equilibrium point so that the sort of mean global temperature will start to increase. Okay, and this is something that's pretty sort of well demonstrated. Here is a really sort of high level plot of CO2 concentration in the black and the mean sort of global temperature in blue below this sort of cutoff point, and then red above that. So basically, the idea here is there's some kind of correlation between CO2 concentration and temperature, right? These are, it's a sort of nice holistic story that we can both talk about theoretically and demonstrate empirically, right? There's data on this, and we know the mechanism with which this happens. But carbon dioxide is not the only greenhouse gas. There are a bunch of other pollutants that also have an effect on global warming. So this is from the most recent assessment report from IPCC on what's known as global warming potential. Okay, so we know CO2 warms the Earth to some extent. And if you set that kind of as the baseline 1, then other greenhouse gases have something known as CO2 equivalent, which is this term right here. CO2e stands for CO2 equivalent. And so here we have methane and we have nitrous oxide. And you can see that a single molecule of methane in a 20-year time period is equivalent to about 80 CO2 molecules. Okay, that's the equivalent effect of one methane molecule. And then with nitrous oxide, that could be 200 to 300 times, 260-ish to 300 times worse than CO2. There's not as much of this that gets emitted compared to CO2, which is why CO2 is kind of the sort of big target for climate change mitigation. But you can see that because of the magnitude of these things, it's also very, let's say, cost effective to think about trying to reduce these as well. And there's been a lot of work in sort of preventing methane, for example, from getting leaked into the atmosphere. One of the things you'll note is that there's something called a 20-year time period and a 100-year time period. And the reason for this, and the reason why it changes over time, is because methane has a much shorter half-life in the atmosphere than carbon dioxide. So if we release CO2 into the atmosphere, it's going to be around for a long time, like on the order of hundreds of years. So there's not much we can do about that now. I mean, there are, if you want to get into the sort of energy side of things, there's talk about like removing carbon dioxide from the atmosphere. So there are possible things, but naturally, CO2 sticks around in the atmosphere a very long time, whereas methane might last 20, 30, 40 years. And that's why over a 100-year time period, this effect decreases. Okay, any questions about this? Yes. What was that? Yeah, so these are kind of unitless. The whole idea is that CO2 has some effect, and they would call this the CO2 equivalent, global warming potential. So whatever CO2 does in the atmosphere, they set it to a baseline of 1, and then these other guys have CO2 equivalent values of this. Yeah. It's a lot of like modeling that goes into figuring, and like atmospheric chemistry and figuring out like effects of these things in how it like traps radiative forcing. Yeah. So just to be clear, the way this works is like, if you, let's say you have 100 tons of CO2, and you have like 5 tons of methane. If you are talking about this in the context of climate change, and you wanted to report like what the sort of global warming potential would be, you could do something like this. it would be, let's say 5. So in 100-year global warming potential, then it would be the equivalent of 100 plus, let's say 5 times 25, which would be 225 tons of CO2 equivalent. So it would be kind of like by mass. Okay. So these are probably the most common ones that we would deal with, especially when we think about the byproducts of combustion that we've talked about so far. So CO2, methane, N2O, these are all going to be things that will contribute to greenhouse gas emissions. Everything else that we've talked about is basically going to be local air pollutants. Okay? And so what are those? So our major air pollutants: carbon monoxide, lead, nitrogen oxides, ozone, particulate matter, and sulfur dioxide, and sulfur oxides in general. Yeah, and so these air pollution can come from mobile sources, right? What we've been talking about with combustion of fuels in like gas cars and diesel vehicles, from stationary sources, from power plants combusting all sorts of fossil fuels, and also from sort of natural sources, right? So burning, wildfires can lead to decreases in air quality that are associated with increases in the presence of these sort of air pollutants. Yes.
I did come seconds late, but I was wondering when the poll when it asked which one of these is the worst.
Yeah.
What do you define by worst? Is worst the one that's the most existing in the atmosphere? Is the worst the one
Okay.
that has CO2 equivalent?
Yeah. Good question. I guess I was thinking the worst by molecule, but I guess you guys would be right. So if I go back here, even though CO2 is not as big as methane or nitrous oxide per molecule, its total contribution to climate change would probably make it the worst. So I guess I will take back what I was saying earlier about like N2O being the worst in this list. It's the worst by the per molecule basis. Yeah. Good question. But then all of these guys were on that poll too, and none of these guys are greenhouse gases. So we'll make sure to keep that straight. Yeah, so let's talk about each of these air pollutants and what sort of terrible things that they do. This actually was who's here in was it the fall before the pandemic?
Yes.
The crazy wildfires? Yeah. So that's the reason why, you know, we had these N95 masks back then, right? That wasn't for coronavirus. That was to make sure that you are not breathing in all of this stuff. So, you know, technically, the sort of way the dose response happens here is it's not that if you are sort of subjugated to a spike in pollution that you'll immediately see sort of deteriorated health effects. Usually these types of things come from long-term exposure, right? And so it's probably still a really good idea to wear a mask when there's like this crazy fire and you have these pollutants everywhere. But generally we start to see negative health outcomes when people are exposed to these pollutants in sort of prolonged time periods. Okay, oops. This thing again. Let me just close out of this so that doesn't happen. All right. So the first one, carbon monoxide. So technically, you guys should all have carbon monoxide detectors in your homes and apartments. I think that's a requirement in either California or in Davis. And the reason for that is this stuff is really dangerous in sort of indoor settings. So carbon monoxide is colorless and odorless. And typically this is going to result from incomplete combustion of fossil fuels. So that's like when your fossil fuel is burning at sort of a non-ideal temperature, or if there are impurities contained in the fuel, that can also lead to incomplete combustion. So carbon monoxide is a molecule that's really similar to oxygen. And so what ends up happening is the hemoglobin in your red blood cells, this is the thing that makes them red, will bind with carbon monoxide. And so the way hemoglobin works, right, in your cardiovascular system is that it binds with oxygen in your lungs and it goes to other places in your body that have a lower concentration of oxygen, and the hemoglobin then releases the oxygen for your cells to use in sort of other ways, right? The problem with carbon monoxide is that when it binds to hemoglobin, it's a much stronger binding. And so it will not release the carbon monoxide, whereas with oxygen it will, right? And so as a result, if you start to saturate your red blood cells with carbon monoxide, it'll essentially prevent you from binding oxygen that your body needs. So it can be poisonous and lead to death. So this is the whole thing, like back in the day, like if you turn on your vehicle in a garage and you kind of sit there, right? There's this, I guess, people would do this to commit suicide. The carbon monoxide poisoning is what's happening here. So primarily this is coming from fossil fuel combustion. So motor vehicles, construction equipment, that sort of thing. But you can also get this from industrial processes and burning wood. And again, generally, this is why burning anything indoors, this is probably the biggest worry associated with that. Oh. Okay, next up, we have nitrogen oxides, NOx. So this is a family of reactive gases that get formed when you have combustion at high temperatures. So what's the most common molecule in air? Nitrogen, right? And so we could avoid this if we had like pure streams of oxygen feeding into our combustion processes, right? But that would be pretty infeasible from a sort of economic basis, right? You don't want giant tanks of oxygen as well. And so combustion today typically relies on just getting the oxygen out of the air. But because air is mainly comprised of nitrogen, one of the byproducts that you commonly get is this nitrogen oxide. And that's because you've introduced a whole bunch of nitrogen into your combustion process. So often appears as a brownish gas. And when we talk about things like smog and like acid rain, NOx is typically a precursor for that. Okay, and so this will react with volatile organic compounds. It'll also react with sunlight in the atmosphere to produce, these crazy organic compounds that we typically associate with smog. Okay, and so this is not great stuff. It's been known to exacerbate asthma. It's associated with heart disease, diabetes, bad birth outcomes, and even increased mortality. It's kind of interesting, right? Like with pollution, it's not like this very acute exposure thing. You might live in the valley in LA, you get exposed to this your whole life, and a whole bunch of people have asthma. It's hard to sort of directly point to say, hey, like this particular exposure led to you getting asthma, right? But we can do things like look at concentrations of NOx in different cities, look at the sort of background levels of a lot of these health outcomes of like asthma, heart disease, mortality. We can look at this in a comparative way to try and get an understanding of the sort of consequences of NOx. This is coming from mobile sources, and we'll see this a little bit more specifically later, but diesel has a pretty big role in producing NOx, and also from power plants. So power plant boilers and turbines tend to emit quite a bit of NOx as well. Yeah, we'll actually look at this exact figure in a little bit, so I'll come back to that. One of the nice things about having an environmental protection agency and a mandate from the legislature through things like the Clean Air Act, there have been a lot of technological requirements to reduce the emission of nitrogen oxides. Okay, and so we can see the change in NOx over time over the last several decades. You can see air quality has improved quite a bit. Yeah, so it's a combination of things. So thinking about vehicles having better emissions controls and getting more efficient, right? And which means that if I go the same distance, I'm combusting less fuel, which leads to lower NOx. And then for a lot of power plants, introducing like scrubbing technologies and ways to reduce NOx from their outflows. Those are, I think, going to be the biggest contributors to this type of reduction that we see. Yeah.
So is that emission over time? So right when it starts, say, how many X years ago?
Yeah. Yeah, exactly. I'm trying to remember when the first year is. I thought it was labeled on here, but apparently it's not. I'll double check. I think it's in the like 80s or 70s. Yeah, up till now. Yeah, it's still continuing to go down. Actually, a lot of this having to do with lower and lower use of coal over time, and more sort of natural gas helps a lot in here, and then with vehicles as well. Yeah. Any other questions about NOx? Okay, sulfur oxides. So most commonly it's SO2, but there can be sort of other forms as well. So this is also a very common precursor to acid rain, kind of together with NOx, right? You can have, what is it? Sulfuric acid, sulfurous acid, nitric acid. This is mainly coming from power plants, specifically coal plants, right? And so with NOx, a lot of the nitrogen is coming from the nitrogen gas that's present in the air. The sulfur here has to come from impurities within the fossil fuels. We don't really have sulfur gases in everyday air. So the most common is coming from sulfur that's contained within molecules of coal. So you'll still occasionally see a little bit of sulfur, like a really small amount in like gasoline or in diesel. But it's really quite uncommon. If you look at the sort of magnitude of emission of these types of things coming from those combustion, it's basically going to be just like really trace amounts. The biggest culprit for sulfur oxides is going to be from coal plants. Also harmful to the respiratory system, as you can imagine, in lots of ways, causes difficulty in breathing, and can react with other compounds to form particulate matter. And the acidity of these sulfur oxides can like physically damage plants. Similarly, so this one's not animated, but this is 2005 to 2007 time period. You can see particularly heavy coal areas here in your southern belt and in the sort of Midwest area, stretching from like Illinois up to Pennsylvania. Lots of SOx pollution. And by the time, even in the sort of early 2010s, it's already starting to look a lot better. And compared to much earlier in the 90s, 80s, those were much worse as well. A lot of the controls at power plants to reduce SOx came out of the Clean Air Act in the 70s. And so since then, the technology to reduce this has improved dramatically. But it's definitely still a problem. You know, this is all a matter of scale, right? But there are problematic areas that have prevalent SOx emissions still today. Yeah.
Noticing on all these graphs that Sacramento / always popular pollution. And also there's that California, like the most popular place.
Yeah. Actually, you know, here even it looks like there's an increase in California. Yeah, I'm not entirely sure why that is.
Could be from when did you say that the nuclear power plants were?
Yeah, that's interesting. Yeah, San Onofre was the really big one that was most recently retired in 2009 and 2011, I believe. So yeah, possibly. Okay. Particulate matter. This is the real bad stuff. So this is, unlike NOx and SOx, which are sort of characterized as these like homogeneous molecules, particulate matter consists of a whole range of different things. And so here we can see a lot of these like ions, organic ions, chloride, nitrous oxide, and SOx are in here as well. But this consists of a whole bunch of other really small things. And it can be sort of these molecular level items. It can be these small sort of Carbon compounds, these are all sort of organic, like acetate, oxalate. And we generally characterize these by size. So PM10, so to give you a sense of size, this blue dot here, that would be the equivalent of a grain of sand. Okay, this green dot here would be the equivalent of human hair. And then PM10, so this is the size of, so one of these yellow dots, so this would be like dust and pollen. And then PM2.5 are these little white dots. So these are, the 2.5 and the 10 refers to the micron size in diameter of each of these compounds. So dust and pollen, PM10, it's not great to be exposed to tons of this, but your body is able to help filter this, right, in your sort of nasal passages. A lot of PM10 size compounds can get captured. So this is considered coarse particulate matter. Fine particulate matter, PM2.5, this stuff can go straight into your lungs very easily. And so when this settles into your bronchi and your lungs, lots of really bad health outcomes. I shouldn't say it goes into your lungs really easily. It goes into your lungs easier than PM10. So this stuff is really bad. It counts for over 4 million deaths annually, and it's the 5th leading risk factor for death. The general rule of thumb is like the dirtier the combustion, the more particulate matter is emitted. And so what that means is like the more impurities you have, the more incomplete combustion that you have, typically, the more of this type of stuff that you would be getting. So distribution of this matter in the US looks something like this, with red being kind of the worst and blue being essentially the best. So particulate matter, as I mentioned, this is definitely kind of the worst for health outcomes, and we can see how it looks throughout the country. And so as I was mentioning, kind of in the basin in California, this is a result of all of the cars in Los Angeles and all of the sort of freight that's happening, right? A lot of that sort of spews into the valley and kind of lingers there. And so you end up having pretty bad particulate matter concentrations in those areas. And then again, correlated with the location of coal plants, we can see a lot of this happening in the Southern Belt and in the sort of Great Lakes region, as I was mentioning before. Yes.
So you say in the valley, what range of area in LA?
Yeah, so I would say it's not just LA, it's like all of Central Valley, you know, Modesto, like Bakersfield, they actually bear the brunt of a lot of the emissions coming in from LA, right? That it kind of moves inland and it gets trapped in that valley between there and the Sierra Nevadas. But LA itself is also really bad because that's like the source of where a lot of this is coming from, because there's just so many cars there. And so even though it moves into the sort of inland valley area, Los Angeles itself is not great. If you have ever driven through LA at nighttime and you look up at the moon, oftentimes you'll see that it's like sort of orange or reddish color. That's because of air pollution and smog. And so the thing is, it's not like PM2.5 and NOx and SOx are all these like really independent molecules, right? This is all coming from combustion, which is why the same places where PM2.5 is really bad is the same places that SOx is usually pretty bad, and the same place where NOx is pretty bad as well. So improvements in air quality for sort of any one of these things will probably improve air quality for the other compounds as well. Okay, so if you guys have like weather apps or specifically air quality apps, or you look sort of online, weather.com, that sort of thing, you guys may have seen something like this, AQI, right? So in Davis, we generally have pretty good air quality, usually, you know, on the order of like 10, 20, 30. And then, you know, for those of you who remember before the pandemic, those wildfires, right, our AQI was jumping up into the hundreds. So what does that mean? Like, what is the air quality index? What does that even mean? So this is essentially a way to generalize air quality and air pollution across all of these things that we just talked about into kind of just one indicator number. Okay, and so what things are included in this index? It includes ozone, particulate matter, carbon monoxide, sulfur dioxide, nitrogen dioxide. So I should mention ozone is another molecule. I don't think I made a slide explicitly on it. It's 3 oxygens, and ozone is also not great either. So it will react with sunlight to form volatile organic compounds. It can combine with a bunch of other sort of combustion products. And oftentimes that's what results in things like particulate matter. Okay. So this is the scale here, generally. Yeah, green, 0 to 50, yellow, 50 to 100. And then all of this stuff, 100 to 500, you probably don't want to hang out and breathe that kind of air for too long. There are cities all around the world, cities in China, cities in India, even cities in the US, where entire populations are subject to orange, red, purple air quality all the time. Okay, and if you look at general rates of like respiratory health and sort of background rates of mortality, you will find that in those cities, it's higher than the average. Okay, and so again, this is something that's really hard to attribute to like one sort of exact effect, but we know on average these things can cause negative health outcomes. Okay, we'll keep going for a second. All right, where are the sources coming from? So as I went through, you know, I talked about some of the sources. This is a more sort of holistic breakdown by percentages of where local air pollution is coming from. So emissions here, you can see broken down by type: carbon monoxide, particulate matters, hydrocarbons, NOx, SOx, and then generally looks something like this. So power production is a big contributor. Agriculture is another big contributor, and vehicular traffic. And then depending on what you're looking at, it can be really different as well. So for example, from transportation, you have a very sort of small amount of this SOx coming from transportation, right? This is mainly from stationary fuel combustion. As I mentioned, SOx is usually coming from coal, right? But transportation accounts for the bulk of carbon monoxide, and contributes roughly similar amounts of NOx compared to stationary fuel combustion. So specific with the exact pollutant, each of these sources will contribute differently. Over time, again, thanks to a lot of the regulatory measures. So in the US, air quality has improved, and we can see how that has happened sort of across a whole bunch of different pollutant types over the last 3 decades. SO2 in particular has been one of the biggest ones, with both technologies that help reduce this out of the smokestack, but also related to just lower amounts of coal being used to produce electricity. Okay, any questions about this? All right, let's do our halftime break right here, and let's reconvene in 5 minutes. So we've looked at a bunch of stuff about the quantity of the air pollution and how that changes over time and how that results from, all these things. And then there is the next step of actually doing some kind of quantification to health damages, okay? And so this is starting to get into the realm of public health. So we observe some emissions happening, and then we go from that air quality to observing these sort of direct health outcomes, right? And so what sorts of things do we get? Heart disease, heart strokes, pulmonary disease. So the vast majority of this stuff is all sort of cardiovascular. And then you've got lung cancer and acute lower respiratory infections, right? And so you also have some respiratory health issues as well. Again, the sort of way in which you can figure out these health outcomes is actually a fairly complex sort of modeling topic. Not my area of expertise, but we rely on a lot of the work in this public health sector to kind of figure out what sort of health damages are coming out of this. In addition to what we see here, which are known as morbidity outcomes, right? So these are things that decrease quality of life and health in general. There are also mortality outcomes, right? So deaths from air pollution. So we can look at a whole bunch of different countries, and we can see, so ambient air pollution here in the brown, okay, in comparison to other sort of mortality outcomes. And so relatively lower in the US, right? But in a lot of developing countries, as I'd mentioned, so thinking about India, thinking about China, these places have dirty combustion processes, both in their vehicles and in their stationary combustion for producing electricity and in industrial applications. And as a result, we can estimate deaths per year per thousands of people, okay? So this, the size of this is basically saying about 1 person in 1,000 people die every year in China due to air pollution. So at a population, a billion, at a population of 1 billion people, you are getting 1 million people dying from air pollution a year in China. In the US, we can see early deaths per year. This is a kind of interesting way that they've organized this, but you can see kind of which state is emitting and which state is, I guess, receiving that air pollution, right? Because some of this pollution can disperse. And we can also see by sector, electric power, industry, commercial, residential, and from road transport, sort of how much of that is coming from there, and then by sort of emission species, if you were to look sort of by state. So this is kind of a interesting visualization that people have done. Yeah.
What is early deaths for
Yeah.
someone dying? Supposed to do that?
Yeah, exactly. But it's yeah, but it can also be weighted by like how many years earlier than they were expected to die. So the next step here, translating health impacts to economic damages. Okay, so we've kind of run through a whole spectrum of disciplines that we need to get from sort of one point to our sort of final outcome, right? So let's talk about what that means. So I started out with understanding issues about, so if I'm talking specifically about gas cars, right, you are talking about understanding some of the engineering aspects of the combustion. And so you might need some engineering background there to understand how much combustion is happening and how much fuel is being consumed, right? You might have to talk to someone who's working in transportation who has knowledge of like travel behavior, right? And if we're talking about electric vehicles, you'd have to think about charging behavior. You might need to have some expertise in like power systems operation and industrial engineering to understand about the emissions associated with combustion from power plants, right? And then from there, you've got emissions coming out of the tailpipe, emissions coming out of the smokestack, and that goes into sort of air quality modeling to understand how those emissions are getting dispersed across different areas, how they're reacting in the atmosphere to form specific pollutant compounds. Then we get into public health, thinking about what sort of health outcomes are coming from exposure to these pollutants. And then ultimately, we think about impacts at sort of an economic level, thinking about the dollars of damages that this is causing. Okay, and so you can see that this kind of field, thinking about electric cars and going all the way to the impacts of electric cars spans this huge set of disciplines. And so there's lots of different ways to kind of be involved here. So this chart in particular, right, we are talking about something you might think about as an economist, where I can sort of translate these damages from my NOx, from my PM, SO2, into some quantified measure. And so here, red means it costs more money, right? Blue means we're going to see some sort of benefits. This is from a paper from a year or two ago that looked at the benefits of electrifying heavy duty freight sector. So changing from your sort of big rig diesel trucks into these big electric trucks. Okay, so the question is, why do we look at the economic damages? Why not just stop at like health impacts? Like, oh, you can avoid this many deaths per year. Does anyone have a sense? Yeah.
Because cash is whatever decisions that are made and make the money at the end of the day. It's not profitable.
Yeah. So I think that's a little cynical way of putting it, but it's generally correct. So let's say, okay, so let's say I have, $10 billion budget for the EPA to pursue some regulatory measures. By having some quantification of impacts, right, I can think in a sort of strategic cost benefit way of applying a policy. Let's say, oh, I'm choosing between this $10 million thing that I can implement here versus like a $20 million thing that I can implement here in another place. And say you can save X deaths and Y morbidity here, and A deaths and B morbidity in this other one, right? Now I have some quantifiable, like monetary damages that I can use to figure out the like best cost benefit application of any sort of regulatory process or like technology implementation, right? And so doing these sorts of calculations helps inform policy because avoided deaths, avoided morbidity is the outcome that you want, but to do it strategically, oftentimes you need to think about putting these into sort of dollars. Okay, so that's why you would want to do it. But then how is it that we actually value health and mortality? So this gets back to our original question, right? So in theory, well, I thought actually most of you guys were going to put like infinite amount of money, but if you were to ask me, like, yeah, sure, like if I could avoid dying, I would pay all my money, right? Would you guys? I mean, if you're dead, I guess what's the use of any of your money, right? So the general idea is that as individuals, when we think about the value of our own lives, we value that essentially infinitely. But in order to do this type of calculation, I would then have to put some kind of monetary value on other people's lives. Yeah.
Knowing the hospitals based off the cost of death.
Yeah, okay, so insurance uses this. Yeah. So this is known as something known as the value of a statistical life. So how would we go about measuring this? So, okay. So who here put an infinite amount when they filled out the poll? Anyone? I know some of you guys did, because it was one of the answers that was. Yes, okay. So you value your life infinitely, which I think is a totally rational thing. But what I'll say is that that I can actually try and use your behavior to elicit the fact that you don't value your life infinitely. Okay, so how did you come to class today? What was that?
By the bus.
By the bus. Okay. So when you rode the bus, were you wearing a helmet? No? Well, why not, right? Like, so in the really minuscule event of an accident in the bus, do you think you'd be safer with or without a helmet? I mean, like you avoid head trauma, right? So, okay, so the whole idea here is if you valued your life infinitely, right, the way that we would, you would minimize risk, right? You minimize risk by probability of like a bad outcome times, so this would be times the damages from that outcome. And then you would take measures to kind of reduce this based off of the relative amount of damages times that probability. So in this particular case, let's say there's like a 0.00000001% chance that the bus would have an accident that would like cave in your head, okay? So it's like, okay, really small outcome. But if you died and you valued your life infinitely, this would be getting multiplied by an infinite dollar amount. So no matter what the probability of the bad outcome here is, you would do everything in your power to reduce that risk, right? But we don't do that, right? We don't wear a helmet everywhere we go. We jaywalk, right? We drive in a car, which there's tons of accidents all the time, right? And so based on the fact that we behave in certain ways and the risk of certain things happening, I can actually go around and elicit kind of the value that we place statistically on our lives based off of like observed behavior. Okay, so that is what's being calculated here. This is not a valuation of an individual life. This is a valuation that we can come up with based off of elicited behaviors for the express purpose of doing these sorts of cost-benefit analyses, which hopefully you guys will see, can see are useful, right? And so in the same way that we don't wear a helmet everywhere, the government doesn't spend all of its money to protect its citizens, right? Taking the entire budget to just like specifically tackle the emissions of like carbon monoxide, right? There has to be some kind of calculus about cost effectiveness based off of this analysis. And it's controversial, right? Value of statistical life. People think about this differently. There is a directive for government agencies to use a particular number, right? But life insurance might pay differently. Other stakeholders might think of this in sort of different ways. And it is controversial that, like, if we think about, if you think really closely about this, it's like if there's like an airplane crash, for example, and then you pay out to the families whose family members, you know, might have perished on the airplane. Are you going to pay like more money to families with younger kin? Do you pay more money to, like, let's say there was a millionaire on the plane, right? And their sort of potential for generating wealth is higher, right? And so this stuff gets really complicated and really controversial very quickly, but still an important topic to think about these impacts. Okay, any questions about this? Okay. So one hot topic is pollution and equity issues, and we're going to dive a little bit more into this in just a second, specifically in regards to electric vehicles replacing gas cars. This is a really hot topic these days, particularly in California. But what I'll generally say is that disadvantaged lower populations typically are burdened more from air pollution. And there's a whole slew of different reasons for why this is. But generally, these are the sorts of differences that we observe in pollution outcomes relative to, let's say, racial distributions and income distributions. Okay, and we'll get a little bit more specific in just a moment. Okay, so sort of honing in on transport, we've talked about all of these things. So gasoline combustion leads to both greenhouse gases and local air pollutants. CO2, methane, and nitrous oxide coming from the GHG category, carbon monoxide, NOx, particulate matter, and then uncombusted hydrocarbons in your air pollution category. CO2, we generally know, is emitted at a rate of about 8,887 grams per gallon of gasoline. This is the official number that EPA uses to calculate emissions from gas cars. But other combustion byproducts can vary depending on, for example, the type of fuel and other sort of conditions. We haven't talked so much about diesel, but since we're talking about air pollution, this is a pretty important topic. So diesel, the difference here, this is a diesel molecule. This is one example of a type of gasoline molecule that you might see. And diesel is a much longer hydrocarbon, so it's more energy dense. This is why larger format vehicles tend to use diesel over gasoline. Okay, so if we're talking about like a big rig truck, right, the reason why they use diesel is because that has the ability to provide enough power for that vehicle. So diesel is similar to gasoline, right? It emits all the same things that I had just shown in the list in the previous slide, but in very different quantities. So here we can see, so diesel vehicles, I think generally tend to be more efficient than gasoline vehicles, especially at higher speeds. So if we think about the sort of optimal range of speeds for a gasoline engine to operate most efficiently, it's usually somewhere in like the 40 to 50 mile per hour speed. Whereas for diesel vehicles, it's usually more closer to highway speeds, like 55 to 70 miles per hour. So these things typically are more efficient. And as a result, they actually tend to emit less CO2. And that's actually a lot of the language that you may have heard in the past about like clean diesel or diesel being better than gasoline is maybe I'll say mildly true in the sense that it's has slightly less CO2 emissions, but I'll caveat that by saying like other people have looked at this and they've shown that that's not true. So I would take that with a grain of salt. It probably depends on conditions and types of vehicles and that sort of thing. But this is like completely outweighed by the fact that the pollutants are way worse. Okay, so if you look at NOx, It's like 4 times higher coming from diesel than from gasoline. So diesel is definitely not cleaner than gasoline. If you ever see that, it's probably from some like truck advocacy group or something. Okay, so let's think about local air pollution from electric vehicles. So no tailpipe. So indeed, you don't get air pollution in the sort of traditional sense, but as we've talked about, right, depending on the upstream source of the electricity, you could be coming from dirty sources or coming from clean sources. So in terms of carbon dioxide, how does this compare? We can see these are by fuel sources. So battery electric vehicles here, depending on the source. So if the electricity production is coming from coal or oil, you are comparable to diesel and gasoline. But again, there are some assumptions being made here that you should keep in mind, like what is the efficiency of these vehicles that they're assuming and the efficiencies of these vehicles. But this is giving a sort of rough estimate. So here, a similar type of chart, more sort of simplified. Gas car, EV charged with coal, EV charged with the current average mix of electricity in the US, and then EV charged with wind. So if a gas-powered car is like 1, this is saying if I charged an electric vehicle straight up with just coal, then it would be actually still lower than a gas car. And then here, this is looking at particulate matter and ozone. And you can see EV with coal is particularly bad, right? Because coal has a lot of SOx, which isn't coming from other ones. And gas here is quite a bit lower than what they're saying with sort of averages. But note that this particular one, petrol here, I believe they're looking at a hybrid version. So it is higher efficiency comparison. So there's a bunch of studies that kind of look at this and do these comparisons. And to maybe better illustrate this point, what's really sort of going on here. So what are and how do we quantify the pollution benefits from switching from a gas car to an electric vehicle? Essentially, this is what we would want to be measuring. And so this is a lot of ongoing research in this area that I'm involved with kind of tries to do this sort of thing. So here's our sort of what we'll call the baseline scenario or counterfactual scenario. So there's a lot of electric cars being sold in the Bay Area in San Jose. It's like the highest density of Teslas in California, right? And so here are the gas cars that they would have replaced, okay? And so you've got a bunch of local air pollution in the South Bay coming from these gas cars. So imagine a world where instead of people buying Teslas, they were buying these gas cars. We measure that in comparison to a world where you replace those gas cars with electric vehicles. Okay, so these guys all have little plugs in the picture. It's kind of hard to see, but these are EVs that are in the same area. And so indeed, what you've done is that you've taken all these cars away, and you no longer have that local air pollution coming from these vehicles, right? And that's the kind of modeling that we would do in this case to measure the air pollution benefits, right? Because we got rid of this and now we have this. So no more local air pollution. But now, as these vehicles charge, there could potentially be pollution coming from power plants. So going back to the equity issues, right? So let's say this power plant right here is providing the electricity for these cars, hypothetically. I am displacing local air pollution here in San Jose, in a sort of, let's say, densely populated place, but also higher income, to maybe another area in California. And maybe there's a power plant located next to like a lower income or disadvantaged community. Those are things that we need to think about to understand the sort of distributive benefits of having certain people adopt electric vehicles. Okay, so going back to these issues of equity, by race, this is looking at the people who are affected and the people who are causing certain emissions across a whole range of different services and use services, right? And so these are things that we use, and then these are the people that get affected by them. And so there is kind of a disproportionate impact of who's using it and who gets affected. So this relates to concepts of environmental justice that California is really trying to focus on during the climate transition, thinking about trying to address some of these issues as well. And so we're doing work to help to understand whether or not electrification is leading to certain outcomes like this. And unfortunately, we don't quite have an answer yet. It's ongoing research. What I will say is that one of the things that I think generally most people agree on is that in the heavy duty freight sector, you're probably going to get really big, like disproportionate benefits. Okay, so a lot of freight corridors pass through disadvantaged communities, and electrifying these corridors can reduce a large amount of local pollution in these areas. So what I'll say is freight accounts for like less than 1% of the total miles being traveled, or sorry, of the total vehicles, not miles, total vehicles on the road, but they account for like 20 to 30% of the miles and energy and emissions. And so making an improvement on that sort of 1% could lead to really big beneficial outcomes to the communities that these trucks are driving through, right? And here, just to kind of reinforce this idea about the freight versus the disadvantaged communities, right? This is kind of colored in here, orange being sort of what we say is a sort of more stressed community. You can see how that correlates with some of the major freight corridors in California. Okay, so kind of to sum all of this up, generally, okay, we know that electric vehicles reduce air pollution compared to gas cars. I think that's sort of abundantly clear from looking at a lot of the data and studies that have examined emissions outcomes of EVs versus gas cars. However, now there's a lot of work to understand the sort of distribution of those impacts and whether certain populations are more benefiting, or in some cases, whether or not populations could even be harmed as a result of electrifying vehicles. Yeah, and all of this is really relevant to allow policy, good policy to develop so that when you push these kind of transition actions through, you're making sure that you're doing it in a sort of responsible way to all communities. All right, so that wraps it up for today. Yeah, if anyone has any questions, let me know. Otherwise, I'll see you guys on Wednesday. And remember, homeworks, I made an announcement on Canvas. It came to my attention that I made a mistake on the homework due dates on the actual assignments, but it's still due on our regular assignment schedule. So Wednesday at midnight.